Recording in progress.
Hello, everyone. This is Fatima Nourouzi. I would like to present one of my research topics as a study of an epidemic SIR model in the sense of Caputo-fractional system at NTA conference. My advisor is Dr. Gaston Gercada from the Department of Mathematics at Morgan State University. In 2019, I've joined NEAR Lab, which is directed by Dr. Gercada, and I could know some of my colleagues, which resulted to write a paper in this research. As an outline, I would like to present some historical background, preliminaries, and then I will give you the problem and my solution, and also the numerical simulation. And at the end, I will present some of the references and with some acknowledgements. As the historical background, what is fractional calculus? Fractional calculus goes to 1695 when L'Hopital asked Leibniz about the meaning of what is the fractional or what is the derivative of y with respect to x when n is not an integer case. In other words, it's 1/2 or any non-integer case. And Leibniz replied in 1695 that it could be an apparent paradox from some useful second sequences will be drawn one day in the future. Until the last 3 decades, this subject remained silent, and during the last 3 decades, we've found some of good applications in some fields such as economics, finance, biology, physics, and so on. Of course, fractional derivative has some advantages. One of the advantages, which is very important, is the local property, means that the fractional derivative does not only depend on the current state, but it depends on the whole specific point of the boundary of the point. And also we have the freedom of choice to choose our classical differential operator. We have the memory effect, which means that the event that we have at the time t not only depends on a specific time t, but also depends on all past historical events. We also have the enlargement of region of stability of dynamic systems, and fractional derivative will provide us more accurate models of real-world behavior. We have some preliminaries, and the first one is the left-sided Riemann-Liouville fractional integral of order alpha. And here we have the antiderivative of alpha, which alpha can be any real integer, fraction, or complex number. The left-sided Riemann-Liouville fractional derivative, which is shown here. And also we have the left-sided Caputo-fractional derivative. And here we have f to the power n of t, which is the nth integer order derivative of f with respect to t. We have the left-sided Riemann-Liouville derivative of a function with respect to psi, and also the left-sided psi-Caputo-fractional derivative. So recently in 2019, Van Terler and Kapelos introduced the very well-known fractional derivative as called Psi-Hilfer fractional derivative of order alpha type beta with respect to another function psi, which unifies all the past definitions that we have. Our problem is introduced as shown as problem 7. We have the SIR as susceptible infectious recovered epidemiological model. we represented this model in the sense of Caputo sense, and we have here S of t as the number of susceptible individuals who become infected at time t. We have I of t as the number of exposed individuals at time t, and also we have R of t to be the number of healed or recovered people at time t. And of course, N of t is the total population. We also represented the reproduction number as R of 0. This number represents the number of people who become exposed to susceptible people. And we want to know how many of the people are getting infected after time t. We first solved the homotopy analysis, and we found the solution after finding the nth order deformation equation with these initial conditions. And also we solved the linear non-homogeneous equation, and after proceeding similarly, we got the pth term of the approximate solution as represented as equation 11. Another part that we did is the existence and stability of equilibria. We put each equation in the system to be equal to 0, and we found 2 equilibrium points, which are E of EQ and E star based on 3 different cases. And for the numerical simulation, we considered these parameters. And if you look carefully, we have the parameter beta, which is the strength of infection, to be low as 0.01, medium as 0.5, and high strength as 0.99. The reason that we chose these 3 different levels of infection is that we wanted to show how much is the stability of the system by using the numerical simulation, and we want to compare the cases. So for the numerical simulation, we used the predictor corrector method of Adams, Bashford, Moulton. We did it in MATLAB using the predictor corrector PI rules, which solves the multi-order system of fractional differential equations by using 3 different cases. The first case, we have all the fractional orders to be equal, and the second and third one, we consider the non-equal cases with different levels of the infection. Here's what we found for the non-equal cases by 2 different levels of the infection as 0.5 and 0.99. As you see here, the system, especially I of t, the number of infected people, are going to stabilize to a fixed point, and we see also S of t goes to reach the fixed point. And we have the same behavior for the non-similar cases, which shows that beta, which is the strength of the infection, doesn't affect the stability of the SIR model. And this paper has been published in Studies in Evolution Equations and Related Topics. And I did this paper with Mr. Yambio in the NEAR lab, and our supervisor was Dr. Gercado. And these are all the references that we have used for this paper. And as an acknowledgement, I would like to say that I'm grateful to be a student at the School of Computer, Mathematical and Natural Sciences at the Department of Mathematics. And also, I'm so grateful to be a research assistant at NEAR Lab, and so thankful to Dr. Gercada, my advisor, for the full support in my PhD journey. Have a great day, and thank you.